Summer, 1992. A young girl takes her position at a lake in Massachusetts. She's a lifeguard. It's a routine summer day. Sun is out. Swimmers are in the water. Parents are on the shore. Everything is exactly the way it should be on a summer afternoon at a public lake. Then she's gone. No witnesses came forward with anything definitive. No one saw exactly what happened. No one could say with certainty who took her or where she went. What investigators had was a crime scene, a lake, a spot where a young girl had been sitting just minutes before she vanished, and evidence. Physical evidence collected from that scene. Evidence that, in a perfect world, would have told them exactly who was responsible. But it didn't. Not in 1992. Not with the technology that existed then. The evidence was collected, processed with 1990s forensic methods, analyzed with 1990s DNA technology, and it wasn't enough. The DNA evidence that was gathered couldn't produce a usable profile with the methods available at that time. The case went cold. The evidence went into storage. And for over 3 decades, a young girl's disappearance remained one of the most haunting unsolved cases in Massachusetts. Right now, more than 30 years after that summer day at the lake, cold case investigators have access to technology that didn't exist anywhere close to what was available in 1992. DNA phenotyping, a technology that doesn't just identify who left DNA at a scene. It can predict what that person looks like, can generate a physical description from DNA alone, eye color, hair color, skin tone, facial features, all predicted from the genetic information contained in a DNA sample. That technology has never been applied to the evidence from this case. Evidence that has been sitting in storage for over 3 decades. Evidence that was collected, processed, and declared insufficient with 1990s methods. Evidence that modern DNA phenotyping technology might finally be able to extract usable information from. This case went cold more than 30 years ago. The evidence was there. The genetic information was there. But the science to read it wasn't. Not then. The science exists now. And it's time for someone to use it. Before we go any further, I need to know something. Where are you watching from right now? Drop your location in the comments. Are you in Massachusetts? Somewhere else in the United States? Somewhere else entirely? I want to see how many people still care about what happened at that lake more than 30 years ago. And if you believe that evidence collected decades ago deserves modern analysis, that DNA technology in 2025 should be applied to every unsolved case where biological evidence exists, that families who have waited over 30 years for answers deserve every possible effort. Subscribe to Cold Case right now. Hit that subscribe button, turn on the notification bell, and smash that like button because it pushes this story to more people who need to hear it. We specialize in cases where evidence was collected but couldn't be fully analyzed when it was gathered. We follow technological breakthroughs that are finally extracting information from evidence that's been waiting years or decades. We track the science that is turning cold cases into solved cases. This case has DNA evidence from the early 1990s that was declared insufficient at the time. Modern DNA phenotyping might change that entirely. And the difference between what 1992 technology could do and what 2025 technology can do is staggering. Now let's dive into what evidence exists, what happened to it in 1992, why it wasn't enough then, and what DNA phenotyping can do with it now. Understanding what happened at that lake requires understanding the context. It was a public swimming area in Massachusetts. Summer, peak season, people everywhere. A young girl working as a lifeguard, doing her job, sitting in her position. And then, in a period of time that no one seems to have fully witnessed, she disappeared. Just gone. From a public lake. In broad daylight. During a busy summer day. The investigation that followed was immediate and extensive. Law enforcement searched the lake area, searched surrounding areas, interviewed everyone who had been there that day, collected evidence from the scene. From the area where she had been sitting, from surrounding areas where someone might have taken her. Biological evidence was among what was collected, DNA samples from the scene, from locations that might have been contacted during a struggle or encounter. Physical evidence that, if it belonged to whoever was responsible, carried their genetic information, their DNA. A biological fingerprint that, if it could be read, would tell investigators exactly who had been there. In 1992, DNA testing was available. It had been used in criminal investigations for several years by that point. But the technology was nowhere near what it would become. Early DNA testing required specific types of samples, required certain quantities, required certain levels of preservation. Samples that were degraded, too small, or not the right type often couldn't produce results. The forensic DNA landscape of 1992 was primitive compared to what exists today. The biological evidence from this case was processed with those 1992 methods, and it wasn't enough. The samples didn't yield usable DNA profiles with the technology available then. They were inconclusive, insufficient. The genetic information was there, locked in those samples, but the tools to extract and read it simply didn't exist yet. The evidence was preserved, stored, kept for potential future analysis. But in 1992, future analysis meant hoping that someday, technology would advance enough to do something with those samples. That someday has arrived. More than 30 years later, DNA technology has advanced in ways that would have seemed impossible in 1992. And one of the most significant advances is DNA phenotyping. Quick question before we continue. What time is it where you are right now? Let us know in the comments. I'm curious how many of you are watching this at night, diving into a case that's been unsolved for over 3 decades, thinking about what modern science might finally reveal from evidence that's been waiting all this time. Let me break down what DNA phenotyping is and why it's significant for cases like this. Traditional DNA profiling compares DNA from a crime scene to DNA in a database or from a suspect. It answers the question, does this DNA match this person? It's an identification tool. You need a database match or a suspect to compare against. If you have neither, traditional profiling tells you nothing about who left that DNA. DNA phenotyping is fundamentally different. It doesn't compare DNA to a known person. It reads the DNA itself and predicts physical characteristics of the person who left it. It analyzes specific genetic markers called SNPs, single nucleotide polymorphisms, that are associated with physical traits. Hair color, eye color, skin pigmentation, facial structure, age estimation, ancestry. From a single DNA sample, phenotyping can generate a predicted physical description of the person who produced that sample. Think about what that means for a cold case. You have DNA from a crime scene, no suspects, no database matches. With traditional profiling, that DNA tells you nothing about who left it. With phenotyping, that same DNA can tell you what that person probably looked like. Can generate a predicted face, a predicted hair color, a predicted eye color, a predicted skin tone. Can narrow down who that person might be based on their predicted physical characteristics. This technology has been used successfully in criminal investigations, has helped identify suspects in cases where traditional DNA profiling produced no matches, has generated predicted physical descriptions that led investigators to people they had no other way of identifying. It's not perfect. Predictions are probabilistic, not absolute, but it's powerful, it's validated, and it can be applied to DNA samples that have been sitting in storage for decades, as long as the genetic material is still intact enough to analyze. The evidence from this case was collected in the early 1990s, over 30 years in storage. The critical question is whether the biological samples still contain analyzable genetic material. DNA degrades over time. How much depends on storage conditions? Temperature, humidity, light exposure, chemical exposure. If evidence was stored properly, DNA can remain analyzable for decades. If storage conditions were poor, degradation might have rendered the samples unusable. But here's what's significant about modern DNA extraction and analysis. The techniques have improved enormously. Methods that can extract usable genetic material from samples that would have been declared completely degraded by 1990s standards. Whole genome amplification can take microscopic amounts of DNA and multiply them to analyzable quantities. Next-generation sequencing can read genetic information from samples that older methods couldn't process. The threshold for what constitutes an analyzable sample has dropped dramatically. Samples that were declared insufficient in 1992, samples that couldn't produce profiles with the technology available then, might now be analyzable. The genetic information that was always in those samples, locked in degraded or insufficient quantities by 1992 standards, might be accessible with 2025 extraction and amplification methods. Even if degraded, even if partial, modern techniques might extract enough genetic material for phenotyping analysis. This is critical. The evidence from this case wasn't just insufficient because of analysis limitations. It was insufficient because extraction limitations prevented the genetic material from being obtained in analyzable quantities. Both extraction and analysis have improved dramatically since 1992. Both improvements matter for this case. Let's talk about what specifically DNA phenotyping would involve if applied to the evidence from this case. First, the biological samples need to be located. They should be in evidence storage, preserved, hopefully under appropriate conditions, for over 3 decades. Locating them, verifying their integrity, and determining whether they're still potentially analyzable is the first step. Second, modern DNA extraction would be attempted, using current methods, not 1992 methods. Current extraction techniques are far more sensitive, can obtain genetic material from samples that older methods couldn't process. If extraction is successful, even partially, the material moves to the next step. Third, if sufficient genetic material is extracted, it goes through amplification. Whole genome amplification multiplies the genetic material to quantities sufficient for analysis. This step is crucial because even successful extraction might yield very small amounts of DNA. Amplification makes those small amounts workable. Fourth, the amplified DNA is sequenced using next-generation sequencing technology. This reads the genetic information, identifies the SNPs, the specific genetic markers that are associated with physical traits. This is where the raw data for phenotyping comes from. Fifth, the SNP data is analyzed using phenotyping algorithms. These algorithms have been trained on large data sets of people whose physical characteristics and genetic markers are known. They use that training to predict physical characteristics from genetic markers. The output is a predicted physical profile: hair color, eye color, skin tone, facial features, age range, ancestry. The entire process, from extraction through phenotyping, takes weeks to months depending on the condition of the samples and the complexity of the analysis. It requires specialized laboratories, expert geneticists, advanced equipment, and significant resources. But for a case that's been cold for over 30 years, for a family that's waited over 3 decades for answers, those resources are justified. If you're finding this information valuable, if you're learning things about DNA phenotyping that you didn't know before, hit that like button. Seriously, every like tells YouTube's algorithm that this story matters. That people still care about what happened more than 30 years ago. That cold cases deserve modern science. Your engagement helps us bring attention to cases that went cold, but might finally be solved with technology that didn't exist when they went cold. Hit like, comment, share. Now let's talk about why this case matters beyond the science, beyond the technology, beyond what DNA phenotyping can and can't do. This case has haunted Massachusetts for over 30 decades. A young girl who disappeared from a public lake on a summer day. The kind of case that stays with a community. The kind that people remember. The kind that families carry with them every single day for years, for decades, waiting for answers that never came. Waiting for a phone call that never arrived. Waiting for justice that seemed perpetually out of reach. The family has lived with this for over 30 years, has carried the weight of not knowing, has watched technology advance, has seen other cold cases solved with DNA evidence, has wondered whether the evidence from their case might someday be enough. Whether someday technology would exist, that could read what 1992 technology couldn't, whether someday the wait would end. DNA phenotyping represents that possibility. Not a guarantee, not a certainty, but a real, validated, proven possibility that the evidence from this case might finally yield information about who was responsible. Information that has been locked in those samples for over 30 years. Waiting. Just like the family has been waiting. Let's talk about the broader implications of DNA phenotyping for cold cases. This isn't unique to this case. There are thousands of cold cases across the United States where biological evidence was collected but couldn't produce usable results with the technology available at the time. Cases from the 1980s, the 1990s, the early 2000s, each one with DNA samples sitting in evidence storage. Each one waiting for technology to advance enough to extract and read the genetic information in those samples. DNA phenotyping changes the equation for every single one of those cases. Previously, unidentified DNA at a crime scene was essentially a dead end if there was no database match and no suspect to compare against. Phenotyping turns that dead end into a lead, a predicted physical description, a starting point for investigation. A way to potentially identify who left that DNA even without a database match. The technology exists, has been validated, has been used successfully, but it hasn't been applied to the vast majority of cold cases where it could potentially make a difference. Evidence sits in storage. DNA sits unanalyzed with modern methods. The connection between old evidence and new technology often isn't made. Someone has to make it. Someone has to look at decades-old evidence and say, this should be reanalyzed with phenotyping. This might finally tell us something. For this case, that hasn't happened yet. The evidence from the early 1990s sits in storage, declared insufficient over 30 years ago, never re-examined with modern extraction methods, never subjected to phenotyping analysis. The technology that might finally read that evidence has existed for years, but no one has applied it to this case. That needs to change. If you haven't subscribed to Cold Case yet, do it now. We follow cases where modern DNA technology is finally being applied to decades-old evidence. When phenotyping generates a physical description from DNA that sat in storage for 30 years, when extraction methods pull genetic material from samples that 1990s technology declared unusable, when the science finally catches up to evidence that's been waiting, you need to know. Subscribe. Turn on notifications. Stay with us. Let's talk about what DNA phenotyping can and can't do, because understanding the capabilities and the limitations is important. Phenotyping isn't identification, it's prediction. It predicts physical characteristics based on genetic markers. Those predictions are probabilistic. They're not absolute certainties. For eye color, predictions are highly accurate. Research has shown phenotyping can predict eye color with accuracy rates above 90% for blue and brown eyes. Green and other intermediate colors are slightly less precise, but still highly accurate. This is one of the strongest capabilities of phenotyping. For hair color, accuracy is also strong, particularly for distinguishing between dark and light hair. Predicting specific shades is less precise, but the general prediction, dark hair versus light hair, is reliable. For skin pigmentation, phenotyping can predict general skin tone ranges: light, medium, dark. This helps narrow the pool of potential suspects significantly. Combined with eye and hair color predictions, it creates a meaningful physical profile. For facial features, phenotyping is less precise but still useful. Can predict general facial structure, nose shape tendencies, face shape categories. These predictions are less accurate than eye or hair color, but still provide investigative value when combined with other predicted traits. For ancestry and geographic origin, phenotyping analyzes genetic markers associated with different population groups, can predict general ancestry, which provides context for other physical predictions. Someone predicted to have Northern European ancestry might have different physical characteristic predictions than someone predicted to have East Asian ancestry. Age estimation is another capability. Phenotyping can predict approximate age range based on genetic markers associated with aging. This is less precise than other predictions but provides useful context. None of these predictions are absolute. None would stand alone in a courtroom as identification, but they create a physical profile, a description that investigators can use, can compare against persons of interest, can use to narrow down a pool of suspects, can use as a starting point for further investigation that might lead to definitive identification through traditional DNA profiling or other methods. For a cold case with no suspects and no database matches, that predicted physical profile is enormously valuable. It's information that didn't exist before. Information that changes the investigative landscape from nothing to something, from a dead end to a lead. Here's where it gets significant. And remember, this evidence has been sitting in storage for over 30 years. DNA phenotyping doesn't just predict current physical appearance, it predicts the genetic baseline. The traits that are determined by DNA don't change significantly over a lifetime. Eye color predicted from DNA at 20 years old will match eye color at 50 years old. Hair color has more variation with age, but the genetic baseline remains. Skin tone predicted from DNA remains largely consistent throughout life. This means phenotyping applied to DNA from the early 1990s can predict what the person who left that DNA looks like today. Not just what they looked like in 1992, what they look like now, in 2025, if that person is still alive. The genetic information doesn't age the way a photograph ages. It contains predictions that remain relevant decades after the sample was collected. For a case this old, that's tremendously significant. Investigators wouldn't be looking for what someone looked like in 1992. They'd be looking for what that person looks like now. Phenotyping applied to 30-year-old DNA can help with exactly that. Can generate a predicted current physical profile that investigators can use in present-day investigation. Let's talk about the specific challenges this case presents for DNA phenotyping. The primary challenge is sample condition. Over 30 years in storage, the biological material could be significantly degraded depending on storage conditions. If degraded beyond the point where any genetic material can be extracted, phenotyping isn't possible. That's the worst-case scenario. But as we discussed, modern extraction methods are far more sensitive than what was available in 1992. Methods that can pull genetic material from samples that would have been declared completely unusable by earlier standards. The threshold question isn't whether the samples were sufficient by 1992 standards. They weren't. The question is whether they contain any analyzable genetic material by 2025 standards. That can only be determined by trying, by applying modern extraction to the actual samples. Second challenge is the quantity of genetic material needed for phenotyping. Traditional DNA profiling requires certain quantities of DNA to produce a profile. Phenotyping has different requirements. It needs sufficient SNP data to make predictions. The amount of genetic material needed might be different from what traditional profiling requires. In some cases, phenotyping can work with less material than traditional profiling. In other cases, it might need more specific types of genetic information. Third challenge is the number of SNPs that can be analyzed. Phenotyping accuracy improves with more SNP data. If only a small amount of genetic material is extracted, only a limited number of SNPs might be readable. That might limit the accuracy of predictions. But even limited SNP data can provide some predictive information. Even partial phenotyping is better than no phenotyping. These challenges are real. They mean phenotyping isn't guaranteed to work on this evidence. But they don't mean it can't work. They mean it needs to be attempted, needs to be tried with modern methods on the actual samples. The only way to know whether the evidence from this case can yield phenotyping results is to apply modern extraction and analysis to it. And that hasn't been done. Before we wrap up, I want to know something. Have you been following other cold cases? Cases where DNA evidence might finally be analyzed with modern technology? Drop the case names in the comments. What unsolved cases are on your radar? What cold cases do you want to see solved? What cases do you think deserve modern DNA analysis? Now let's piece together what happens next in a case like this and why the path forward matters. The path from cold case evidence to phenotyping results isn't automatic. It doesn't happen without someone initiating it, without someone deciding that 30-year-old evidence deserves modern analysis, without someone allocating resources, obtaining the samples, commissioning extraction and analysis, interpreting results. Each step requires human decision and human action. Who makes those decisions? In most jurisdictions, it's the detective or investigator assigned to the case, working with the prosecutor's office, with input from forensic laboratories. Cold case detectives are often the people who push for reanalysis of old evidence. They review cases periodically, look for new approaches, consider whether technology has advanced enough to warrant retesting evidence that was previously declared insufficient. In some cases, families push for reanalysis, advocate publicly for modern testing of old evidence, apply pressure through media, through advocacy organizations, through legal channels. Family advocacy has been a driving force in many cold case reopenings. In this case, the family has remained active, has kept the case in public awareness, has continued to demand answers. Forensic laboratories also play a role. Some labs proactively reach out to law enforcement about cases where they might be able to offer new analysis capabilities, particularly for high-profile cases, cases that have significant public interest and media attention. DNA phenotyping companies themselves sometimes get involved, particularly for high-profile unsolved cases. Some offer pro bono services. Some work with law enforcement to identify cases where phenotyping might be applicable. The technology companies that developed phenotyping understand its potential for cold cases and have incentives to demonstrate that potential. The convergence of family advocacy, cold case detective initiative, laboratory capability, and phenotyping company involvement creates the conditions under which reanalysis happens. For this case, all those conditions exist or could exist. The family is engaged. Cold case resources exist. Laboratory capability exists. Phenotyping technology exists. The missing piece is the decision to connect them, to apply the technology to the evidence, to try. After more than 30 years, the case is still open. Justice is still possible if the evidence yields results. The biological samples, if they still contain analyzable genetic material, could potentially tell investigators what the person who was responsible looks like. Not a name, not an immediate identification, but a physical description, a predicted profile, a lead that has never existed in this case before, a lead that 30-year-old evidence might finally produce if modern technology is applied to it. If you haven't subscribed to Cold Case yet, what are you waiting for? We cover cases just like this one. Cases where evidence collected decades ago is finally being re-examined with technology that didn't exist when it was gathered. Cases where DNA phenotyping, AI analysis, modern forensic techniques are turning decades of dead ends into leads, into evidence, into justice. And you don't want to miss what happens when evidence from the early 1990s is finally analyzed with 2025 technology. Hit that subscribe button right now. Turn on notifications. The science is moving forward. The technology is proven. The evidence exists. Everything needed to potentially extract information from 30-year-old DNA is available. What's needed now is for someone to make it happen for this case. And when they do, and the results come in, Cold Case will be here to cover every development. We've covered a lot of ground today. More than 30 years of waiting. Evidence collected in the early 1990s that couldn't produce results with the technology available then. DNA that was declared insufficient by standards that have been completely surpassed. Extraction methods that have improved dramatically since the samples were collected. Phenotyping technology that can predict physical characteristics from genetic material. Technology that can generate a physical description of whoever left that DNA at that lake more than 3 decades ago. This case represents both the failure and the redemption of our justice system. It went cold. The investigation stalled. For over 30 years, it seemed like answers might never come. But the evidence was preserved. The samples were kept. And the science kept advancing. Year after year, decade after decade, until the technology that might finally read that evidence exists. until phenotyping can do what no technology could do in 1992, until the wait might finally be over. She was a young girl who disappeared from a public lake on a summer day in Massachusetts. She had her whole life ahead of her. She had a family that loved her. She had a community that knew her. And she deserved to come home. She deserved safety. She deserved a life that wasn't taken from her. She deserved justice that didn't take over 30 years to potentially arrive. Instead, she was taken. And for over 30 years, her family waited for answers, waited for the phone call, waited for the breakthrough, waited for technology to advance enough to read evidence that was collected at the beginning of their nightmare, waited for someone to apply modern science to old evidence and finally extract the information that was always there. But their story isn't over. After more than 30 years, the evidence that was collected might finally mean something. The DNA that was gathered, preserved, and declared insufficient over 3 decades ago might finally be analyzable, might finally yield a physical description of whoever was responsible, might finally give this family a lead that has never existed before. A lead that 30-year-old evidence, analyzed with 2025 technology, might produce. She can't be brought back. That's the tragedy no technology can undo. And we can't give her family back the 30 years they spent waiting for answers that never came. But we can ensure that the evidence from that summer day is analyzed with the best available science. We can ensure that DNA phenotyping is applied to samples that have been waiting over 3 decades. We can ensure that if the genetic information is still there, locked in those samples, modern technology extracts it. We can ensure her story is told, her case is pursued, and her memory is honored with the scientific effort her case deserves. This case was cold for over 30 years. The evidence was there. The genetic information was there. But the science to read it wasn't. Not in 1992. The science exists now. DNA phenotyping can predict what the person who left that evidence looks like, can generate a physical description from genetic material that was declared unusable 30 years ago, can turn a dead end into a lead, can turn 30 years of waiting into the beginning of justice. The technology caught up, the evidence survived. And now there's a path forward that didn't exist for over 3 decades, a path that starts with applying modern extraction and phenotyping to evidence that has been waiting for exactly this moment, waiting for exactly this science. Rest in peace. After more than 30 years, the science that might finally bring answers to your case exists, and it's time for someone to use it. If this cold case moved you, if you want to see modern DNA technology applied to evidence that's been waiting over 3 decades, if you believe 30 years is too long to wait when the science to potentially answer questions finally exists, don't forget to hit that like button and subscribe to Cold Case. We're tracking developments in DNA phenotyping and its application to cold cases in real time. Leave a comment with your thoughts. Do you think DNA phenotyping should be applied to every cold case where biological evidence exists? Do you follow other cases where modern DNA technology might make a difference? What unsolved cases do you think deserve this kind of scientific attention? And share this video with anyone who follows cold cases, anyone who believes that evidence should be analyzed with the best available science regardless of how old it is, anyone who wants to see decades-old cases finally get the technological attention they deserve. She waited over 30 years. Her family waited over 30 years. The evidence waited over 30 years. The science finally caught up. The wait might finally be ending, and when it does, the truth that's been locked in that DNA for over 3 decades might finally come out. Technology didn't exist in 1992 to read it. It exists now, and it's time to use it.